This is the Flight Dynamics Albatross briefing by Henry Sanders. The first part of this briefing considers the weight and balance of the Albatross, and this includes comparing the actual CG location of the Albatross with the measured CG location. And you can see this provides a linear, a straight line that does not quite go through the origin, but provides us with the aft CG limit of 0.158 meters and the fore CG limit of 0.3375 meters. Anything out of these bounds, and the aircraft cannot even stand on its landing gear. The thrust measurement includes looking at the relationship between the revolutions per minute and the thrust. To do this, unity was used in the static thrust mode, and the revolutions per minute of the aircraft were increased incrementally, and the static thrust was measured at each revolution per minute, allowing this to be plotted, allowing us to understand the relationship between the revolutions per minute and the static thrust. This graph also suggests that the maximum static thrust is around 28 newtons. The flight control configuration is shown here, and this includes the roll, pitch, yaw, throttle, and flaps for both ailerons, elevators, props, and flaps. And you can see that this is used for ensuring the pilot can control the aircraft in a way that the test can be completed. The longitudinal dynamic response to controls are shown here. So the variation of elevator deflection angle and angle of attack with time are shown in the left diagram. When the elevator angle is deflected to minus 15 degrees, the angle of attack is around 15 degrees, showing a directly proportional response to the change in elevator angle. And then the angle of attack against time is also shown in the top right, which is allows us to see the response from different airspeeds of the Albatross. So at higher airspeeds, like 50 meters per second, once the flaps are returned back to the baseline angle, the aircraft returns to the 6-degree angle of attack faster than it would for the 10 meters per second airspeed. As you can see there, the 10 meters per second airspeed, it actually dips below slightly, and it's less damped than the higher airspeeds. The variation of angle of attack for different CG locations is shown in the bottom right. For the CG locations that are closer to 0.1, the baseline angle of attack is higher and around 7 to 8 degrees. However, for the CG location of minus 0.05, the angle of attack is around minus 5. The lateral dynamic response to controls is shown here. So as the aileron angle is increased up to 30 degrees, the roll rate is increased up to around 60 degrees per second. This can be expected as increasing the aileron angle increases the lift produced by each aileron, and therefore increasing the rate at which the aircraft can roll. The top left to top right diagram shows the time it takes for the aircraft to complete a roll. And for the 30-degree case, it's a much lower time, and this is because the lift is higher and the roll rate is faster. The yaw and the pitch stability are shown below as well. So the yaw is less stable than the pitch. The yaw, you can see there, is not very damped as it resonates around the baseline level, and the pitch is more critically damped. And this is a result of the pitch movement of the aircraft having higher lifting surfaces. The zero thrust pitch line is located at the point minus 0.05 from the coordinate system. And while completing the thrust line tests, it was visible that if the CG was below the thrust line, there is a resultant downward pitching moment, and if the CG is located above the thrust line, there is a resultant upwards pitching moment. The flight performance is characterized by the lift curve slope in the top left, and the lift curve slope allows us to see that for the flap at 40 degrees, the maximum CL is 1.24, and this is at an angle of attack of 15.5 degrees. When the flap is at lower angles, the lift coefficient is much lower. The drag polar is then shown in the right. However, for past 0.15, the stall characteristics start to begin, so that graph can be ignored from about a drag coefficient of 0.15. The maximum glide ratio is 13.58, and that occurs at a CL of 0.51, shown by the graph at the bottom of this page. The longitudinal trim is shown here, and this compares different elevator angles and the response by the moment coefficient and the lift coefficient. And you can see there that they all have the same shape. However, it's the vertical displacement that is changed. So for lower elevator angles, the moment coefficient is more positive and higher. However, at 40 degrees, it is lower and far more negative and produces more moments on the aircraft. The longitudinal stability is characterized by the graph below, and this allows us to estimate the neutral point, which was estimated at 0.1 meters, so 10 centimeters from the origin of the coordinate system used in this simulation. And this was found using the intersection of these lines. The ground handling is shown in this video, and the maximum safe ground handling of the Albatross was around 10 meters per second, and anything more than this could be taxied at around 14 meters per second. However, at 14 meters per second, it's less safe and more risky for the pilot. The minimum up-stick speed is shown in this video here, and the minimum up-stick speed is the minimum speed required for the aircraft to actually take flight. And as you can see, for the Albatross, it is around 16 meters per second, shown in this video here. The cruise trim is shown in this video, and this is where the aircraft is flying at a constant altitude, constant velocity, and the throttle is not being altered. And for this, the throttle setting was at 24% of the maximum RPM, and the elevator trim setting was at -8 degrees. The minimum trim flight speed allows us to understand how slow the aircraft can go before it cannot fly anymore. And for the Albatross, this was at 14 meters per second. So when flying the aircraft, it's useful to tell the pilot that it's around 18 meters per second, as this provides a safety factor and avoids any catastrophic failures for the aircraft. The maximum trimmed flight speed is shown here, and this was the opposite to the minimum in the sense that it was a constant altitude. However, the RPM was set to the maximum, and this provided a maximum trim flight speed of 74 meters per second. The phugoid frequency was measured using the experiment shown on the right. So this was a large disturbance in angle of attack, followed by no input from the pilot to understand the recovery of the aircraft. And the phugoid frequency in this case was 0.0769, which was found using the differences between these two peaks. So you can see there, no input is being input by the pilot. However, the aircraft is still going up and down. And finally, once all these tests have been completed and the trim settings have been found, the flight test circuit could be done, shown here. And this included weaving in and out of the pylons at the Lambeda Aerospace Centre. You can see here that it's much more stable flight, and this is a result of using the trim and the different dynamic properties of the aircraft discussed in this video.